Hi, my name is Ilaria Luna. I'm from Washington, D.C., and we are the C's Analog Research Group, here to introduce our own analog design called HELIX.
Hi, I'm Amogh Badrayani and I'm from Austin, Texas.
Hi, my name is Raul Garcia and I'm from New York City.
Hi, my name is Andrew Gordon and I'm from Boise, Idaho.
Hi, my name is Herndon and I'm from Los Angeles, California.
Hi, my name is Richard Lian and I'm from Louisville, Kentucky.
Hi, my name is Tyra, Lovell, and I'm from Round Rock, Texas.
Hi, I am Ben Major and I'm from Coonersville, North Carolina.
Hi, I'm Hannah Murphy and I'm from Chilton, Wisconsin.
Hi, I'm Josue Zambrano and I'm from Frederick, Maryland.
The analog we created is named HELIX, which stands for Human Exploration Long Duration Interplanetary Expedition.
Alright, let's talk about the purpose of HELIX. HELIX is used to simulate a Mars mission, a transit mission to Mars, residency on Mars, and a transit back to Earth. Now let's talk about some goals we want to achieve in this analog. The first one is resilience of off-nominal events. For example, Cascadian failures, rising temperatures that can cause other issues, actual dangers such as tank explosions. The second is psychological and physiological effects, being isolated in an unknown area for a long time. The third is teamwork capabilities, working with the team to complete tasks. The fourth one is to simulate a self-sufficient environment on Mars, living there while in face of limited resources. And the last one, support robust human robotic and human AI interactions, for example, talking to an AI family.
Since we are doing an analog, a complete mission to Mars, we plan on placing our analog on the world's most Mars-like terrain. The climate that most closely resembles Mars is Devon Island, Canada, located in Baffin Bay, which is the world's largest uninhabited island. Devon Island is similar to the habitat of Mars because of the explosive craters, volcanic formations, and the barren and rocky terrains. The surface of Mars consists of craters, volcanoes, and dry lake beds. The remote location of our analog gives crew members the feeling that they are away from people, but in reality they are really just across the water. The location of our analog gives crew members easy access to help if they need it along the mission. The climate of Devon Island varies depending on the time of the year. Devon Island has long winters with temperatures reaching negative 122 degrees Fahrenheit. On the flip side, Devon Island has shorter summers with temperatures averaging only around 41 degrees Fahrenheit, which is similar to the climate of Mars due to the fact that Mars ranges from temperatures of 70 degrees Fahrenheit to negative 225 degrees Fahrenheit.
The HELIX analog will take place over 365 days, with each day in the analog representing 2 days on Mars. The 7 stages are as follows. Day 1 through 74 will be capsule and transit time to Mars. Day 75 through 217 will be the crew actually living on the Mars base. And then day 218 through 365 will be the capsule and transit back to Earth.
So now we'll be discussing about the crew requirements. We'll be looking for a crew size of 8 members, and for the following qualities: to have passed a Class 2 flight physical examination, to be scuba certified in order to perform EVA tasks, be a U.S. citizen, and to be within 30 and 60 years of age. Mission Control will be looking for any qualities deemed valuable for the analog, such as previous military experience, previous or current STEM careers, involvement in extreme conditions/environments, or team experiences of any fields. Continuing with the crew requirements, we'll be looking for the following for ideal conditions: 1 crew member with a doctorate in medicine, and 1 crew member with 4 or more years of psychiatrist experience. We look for these 2 qualities in order to prevent any external contact with the analog team inside to replicate an environment most similar to a real space mission. We seek for the other 6 crew members to have a bachelor's degree in any science or engineering field, along with 2 years of experience in their career. Experience could be in military or in science and engineering job. Or we seek for the 6 crew members to have a master's degree or PhD in any science or engineering field.
Here we have the final design for the Helix analog. As you can see, it is made of 3 wings and a trigonal planar pattern. One of these is dedicated to living, one is research, and one is hygiene. You can also see the 2 cube-shaped airlocks on either side of the analog to allow the astronauts to enter and leave the habitat. There is also a capsule for the initial launch and descent from this transit vehicle, and a storage capsule to contain any extra materials that the astronauts may need. There's also a solar panel array to power the habitat, and of course this is the transit vehicle that will carry the astronauts for 72 days twice. This is our first module, the hygiene module. As you can see, it contains 2 toilets and 2 showers. This is due to the large crew size so that everyone can get everything done in a timely manner. We also have a sink connected to a water storage tank. That storage tank is connected to another one farther on in the analog so that we have enough water for the entire journey. You can also see on the far left that we have a waste disposal unit that will get rid of any solid waste, and that solid waste is generated through our water recovery system, similar to the one on the ISS. This will remove any water from waste as well as the air. This is our living module. It first and foremost contains a medical bay for the doctor to work in case any injuries incur. It also includes the exercise equipment, which is crucial for crews to survive healthily in the zero-gravity atmosphere. It also contains the capsule dock, where the astronauts will originally get in and then leave this transit vehicle. And then it contains 8 bunk capsules, each of which is soundproofed for privacy reasons, as we found that was very important to astronauts in our research. And finally, we have our labs and storage module. The storage module, of course, will store all of the resources the astronauts need, and the lab module contains 2 research tables that are empty for the astronauts to use for any purpose they may need, 2 computer stations, which contain a total of 2 desktop computers and 8 laptops, so that the astronauts have as much computing power as they need, as well as a water station and food preparation equipment, including a microwave to allow the astronauts to eat. There are also spaces for larger research devices that may be needed, and of course an airlock connector.
Neutral buoyancy occurs when an object has neither positive nor negative buoyancy. The object will have the tendency to neither float or sink. Neutral buoyancy is created by adding weights to the astronaut. This ultimately simulates microgravity because heavy objects can be manipulated in a neutral buoyant environment. Simulating microgravity will allow the HELIX crew to perform EVAs or extravehicular activities. EVAs are significant because it will be necessary, especially during a long-duration mission such as the mission to Mars, that we are able to replace any of the failed hardware components external to the vehicle. The pool will be in an enclosed building, and entry will be through a tube containing a ladder that is connected to the capsule. Infrastructure will be constructed to hold the neutral buoyancy pool. Much like the Neutral Buoyancy Lab, or NBL, the temperature of the water will be regulated at 82 to 88 degrees Fahrenheit so that divers will not be impacted by hypothermia. Additionally, just like the Neutral Buoyancy Lab, the water will be recycled every 19.6 hours. Precautions that need to be taken to ensure the safety of the crew members include having 2 divers per person. These divers will be on standby. Each crew member will also be required to be a certified diver. Layouts to establish neutral buoyancy will take place in the airlock. Additionally, not all crew members will partake in EVAs at the same time. A medical team will also be present in case of any emergencies. In case of decompression sickness, a hyperbaric chamber will be available. Additionally, the airlock will be used as a decompression chamber in order to prevent decompression sickness.
Hi there! Our neutral buoyancy pool will have to be both saline and chlorinated. The salt will make sure our astronauts float, and the chlorine will keep it clean. Because of these highly corrosive conditions, our traveler stage will have to be extremely resilient. Stainless steel can handle the pull, unlike other metals such as aluminum or carbon steel. A resistant coating should help as well. The windows will use polycarbonate. Polycarbonate is perfectly clear, half the weight of glass, and 250 times stronger. The only drawback is that it scratches relatively easily.
This is our online habitat where the astronauts will simulate living on Mars for 217 days. The habitat is located on Devon Island in Canada. As you can see, the habitat is separated into 3 distinct areas, which are designed to psychologically separate the working and living aspects of astronauts' time. This first area will be the living quarters with 2 floors. The first floor will be open space where the astronauts can have recreational time and public workspace. They will also have a eating space where astronauts can socialize and consume food, along with a kitchen where they can store and prepare food. The second floor will contain 8 bedrooms where the astronauts will be sleeping. The rooms will be soundproof for privacy reasons and keep personal items of the astronauts. The other areas will contain a research and medical zone. The Fab Lab will be a place where things are going to be 3D printed to solve problems. The Human Robotics Lab will be a place for rover and drone controls. The AI Center will be for simulating human interactions with artificial intelligence. The Med Bay will be for the doctor to work in and help mitigate any injuries that may occur. There will be research offices for conducting experiments and working on the planet. Exercise space to keep astronauts healthy in the 30% gravity.
Our solid domes will be made of lavacrete, similar to trapea. Closed cell insulation will be used in the walls to reduce heat loss and sound. The clear dome will use an aluminum and polycarbonate lattice. Aluminum is lighter than other metals, such as steel or titanium. It also has the advantage of being unable to rust. One bonus is that polycarbonate blocks UV, so no sunburns.
One of our analog's main purposes is to develop methods for the crew's self-sustainability, both in the transit vehicle and on Mars. Most importantly, the crew will experiment with various methods of hydroponic systems, such that they can have different types of food in their diet and fresh plants that will help boost their morale. Once they do arrive on Mars, however, we will be experimenting with different crops that they can grow on simulated Mars soil on Devon Island so that they can test other types of nutritious foods that will help vary their diet. Of course, hydroponics especially requires a large amount of water, so we will be implementing the same water recycling and purification system that is currently in use on the ISS, so that they can recycle up to 98% of the initial quantity of water they will be bringing. Another type of diversification of their diet that we will be implementing is fish eggs, so we will attempt to cryopreserve them throughout their transit time and then thaw them so that they can have some more variety in their diet. And of course, we're going to be using the local resources that we will find on Mars, such as the surface ice, to help supplement their water supply. And lastly, to help limit the amount of pollution and space debris we will be creating, we will try to implement a zero waste policy where we will implement compostable materials so that we don't pollute the planet. And as you can see, we also have other experiments such as planned off nominals, and we will be monitoring the psychological effects of isolation on our crew, similarly to many other analogs.
With long-term travel to the Martian planet, communications are the largest issue. Radio signals take 5 to 20 minutes to reach from Earth to Mars, depending on the planet's positions. Therefore, HELIX will allow for family contact between crew members and their families. But a one-way 20-minute communication delay will be applied whenever there is contact to account for a worst-case scenario in the astronaut's training. Next, human-robotic interactions will be studied. Due to the bandwidth demand required and its limited access, medical and family conferences will be available, but limited. Therefore, HELIX will study the use of robotics and virtual reality technology to allow crew members to meet their families asynchronously while maintaining a feeling of physical setting through a virtual reality world. The psychological effects and effectiveness of using virtual reality as a means of family and medical communication will be closely monitored by NASA scientists.
So why HELIX? What makes our analog special and different from the others? Well, for starters, HELIX encapsulates an entire mission to Mars, starting with the trip to Mars, then the actual stay on the planet, and lastly, the return back to Earth. This differs from other analogs, which may only contain one part or aspect of a whole mission. In addition, the crew will have experience living in both space and Martian environments. The HELIX mission will also include a neutral buoyancy lab to simulate Mars and spacewalks, which has never been done before. HELIX will provide NASA with the necessary physical and psychological data for future missions to the Red Planet.
Our time at SEAS was truly unique and a life-changing experience that allowed us to forge connections in the aerospace industry and foster a deeper understanding and appreciation for space, science, and engineering. SEAS also expanded our knowledge of the careers truly available to us in the future. These past few weeks have changed all of our lives for the better.
These past few weeks would not have been possible without the help of a few very important people, among which, of course, our mentor, Mr. Petty, who was an invaluable member of our team. Then we have Mr. Stewart, who was so kind as to share his experience as a crew member in multiple analog missions. And of course, Ms. Baggio and Ms. Miller, who were both program managers for SEAS.
Thank you from Team HELIX!